Hello. In our previous chats, Dr. Peng shared the design history of SRv6. Now we're going to look a little deeper into that SRv6 design. Dr. Peng?
Simply speaking, SRv6 is a combination of SR and IPv6. As defined by relevant standards, SRv6 enables segment routing to be supported in the IPv6 data plane.
Why do we still need SRv6 after the emergence of SR?
SRv6 has all the advantages of SR, and because SRv6 is based on IPv6, it inherits the native programmability of IPv6, making networks programmable.
Can you explain network programming for us?
Let's use an analogy. Think of network programming in the same way as computer programming. In computer programming, we use a programming language to convert our intent into a series of instructions that computers can understand and execute to meet our needs. Similarly, network programming converts a service intent into a series of instructions that need to be executed by the devices along a network path in order to meet the custom requirements of services and guarantee the SLA.
Dr. Peng, I know that you are heavily involved in promoting SRv6 standards. Are there any important insights you can share with us?
In general, SRv6 standards promotion is moving very fast. Currently, all drafts regarding basic SRv6 features have been accepted by the working group, and some of them have already been released as RFCs. There are also some drafts that have passed the last call of the working group and will shortly be released as RFCs. In fact, SRv6 Standards promotion is closely related to R&D. At the beginning, basic SRv6 R&D was completed in carriers' labs based on the existing version of the corresponding draft, and then cross-vendor interoperability tests were conducted. According to the test results, the draft was updated by extending relevant protocols. 5 rounds of tests were performed in total, achieving real interaction between standards and R&D. This indicates that SRv6 ushers in a new mode of standards innovation in the IETF.
The development of 5G services places higher requirements on network connections. To meet these requirements, packets need to carry more information, which can be achieved through SRv6 Programmability.
You're right, and in regard to this, we need to talk about SRv6 encapsulation. Each SRv6 packet is encapsulated with an SRH, as defined in RFC 8754. The multidimensional programmable space offered by SRv6 is mainly represented by the SRH. First, the SRH enables network nodes, links, and service functions to be uniformly programmed as an explicit path, guaranteeing the SLA. Next, each SID is programmable and consists of locator, function, and arguments fields with variable lengths. The arguments field can carry information to be parsed by corresponding SRv6 nodes. Finally, SRH TLVs can carry metadata information for SRv6 nodes. For example, SRH TLVs can be used to collect performance measurement information.
Some services, such as 5G telemedicine and power differential protection, require low latency paths, while other services like video backhaul require high bandwidth paths. How does SRv6 meet the SLA requirements of these different services through path programming?
Before answering this question, I need to explain the entire service process. Network information, such as topology, available link bandwidth, and latency information is collected and then sent to a controller through protocols. Based on the specified constraints, the controller computes the optimal path through the corresponding algorithm and delivers the path to the ingress. According to the requirements of different services, the ingress performs intelligent path selection and steers traffic to corresponding SRv6 paths, guaranteeing the SLA.
With the development of cloud services, service processing locations are becoming more flexible. Some cloud services further break the boundary between physical and virtual network devices. All of this changes the scope of network connections. At MWC Shanghai 2021, intelligent connectivity and cloud network convergence were mentioned during the Huawei Forum. Can you tell us how SRv6 promotes cloud network convergence?
Currently, MPLS doesn't support cloud access and probably won't in the future. Given that SRv6 is based on the IPv6 data plane, protocols between the cloud and network can be unified, laying a foundation for SRv6 to support cloud network convergence. In addition, SRv6 has been supported on Linux since Linux 4.10, enabling SRv6-based cloud access and end-to-end implementation.
So, with the passage of time, SRv6 has proved to be a future-oriented technology?
Indeed. From the perspective of the entire IPv6 enhanced technology system, SRv6 belongs to IPv6 enhanced 1.0. It can be used as a basic transport protocol that supports the IPv6 enhanced technology system. It can also be oriented to 5G and cloud services to effectively support more new types of network services such as network slicing, IFIT, and APN6. Simply put, as a future-oriented technology, SRv6 can better support new types of services and meet their requirements.
Thank you, Dr. Peng, and thank you for watching.